This video demonstrates a visual solution to quiz number 2's final problem. So I've already set up a GeoGebra applet to be able to model the situation. The blue function f here is the piecewise function, or a function similar to the piecewise function that you saw in the last problem of quiz 2. Notice I've added a couple of features. I made this slider, and I also added this point a. This a value measures the integral of the function f, the blue function, from x equals 2 to b, where b is this slider value. Notice that I set this integral value to start at 2. That was a common error I saw in the quiz, that people thought that the area accumulation function started at 0, but it starts at 2 instead, which makes it a little bit more complicated. So let's see what happens. I'll just press OK. So now when we consider, so our integral is starting at the value x equals 2, and as our b slider progresses to greater values of 2, notice that, here, let me move. Notice that you see this area, because the function f is positive, this area that's being accumulated is also going to be positive. And this is the way that in my head, I don't need a GeoGebra applet to visualize what's going on here. But I see that as b increases, for an x value of 3, we've accumulated an area of 4, and that area grows and grows and grows all the way until x equals 4.5. That this is sort of the biggest amount that we can get. It turns out the area under this curve from x equals 2 to x equals 4.5 is exactly equal to 9. But if I go past 4.5, notice that my function f dips below the x-axis, and that means that my total area accumulation function is going to start accumulating negative values. So seeing as b progresses, I'm having to compensate by subtracting out these areas below the x-axis, and it means that if I were to continue going all the way until x equals 6, that my area value drops down to 4, because I've had to subtract out all of this area below the x-axis. Similarly, going backwards, we can evaluate. So what does that tell us? So that tells us the maximum value of the function, actually, that the most area that I can possibly accumulate is up until x equals 4 with an accumulation value of 9. How do I find out what the minimum value of the function is? Well, a possible candidate would be out here at x equals 6, because we see that we started accumulating positive areas and it got up to 9 and then it backed down to 4. But notice that an area of 4 is still a positive area. That's still a pretty big value. That a smaller value would be just back here at 0. If b equals 2, then the total accumulated area is 0. This is a rounding error. But we can do better than that. We can get a smaller value than 0. A smaller value than 0. Consider what happens if we start accumulating backwards area. I realize that that's not a precise mathematical term, but this function is still above the x-axis, so we do typically think of this as a positive area value, but we're moving backwards because our starting point is 2, and now we're integrating from 2 to some value that's less than 2. So this accumulated area is going to be a negative area, and in this case, if you go backwards to b equals negative, or b equals 1.5, we see that we get an area of -1. If we continue moving backwards from here, however, a weird thing happens. So here's the accumulated area as -1. If we keep going backwards, our accumulative area starts increasing again. What's going on here? These are areas below the x-axis, so typically we think of them as negative areas. But because we're moving backwards, a negative area becomes a positive value for my accumulation function. So as I'm moving backwards through this section of the graph, I'm actually increasing the value of accumulated area, thinking of this as my starting point, moving backwards and accumulating these negative areas. So as I move backwards this way, you see that when I get to the start, I actually have an accumulated area of +4, because right here at x equals 1, the positive and negative pieces cancel out and I'm at 0. And continuing to move backwards on these negative areas gives me positive areas and a positive value of 4. So that was a lot of talking, but I think that it's a good analysis to think through, and GeoGebra does a nice job of visualizing what's going on. A second thing that I want to do, that I wouldn't expect you to do to be able to solve the problem, that I want you to be able to visualize this process without using GeoGebra. This is definitely a type of question that you're going to see on the first midterm. But something that GeoGebra does allow us to do, I created this point B over here. So this B point is a function that has an input of my slider value and an output of the area accumulation function. So really this is the graph of B of x. And you can see as I move my slider, as I move my slider, that my point B changes in value. And this is the graph of the area accumulation function. Really, this is the antiderivative of this piecewise blue function that we had before. Notice that where my blue function is flat and constant, I have a linear curve. Where my blue function is linear, I have these small parabolic pieces, and then it becomes linear, and then parabolic again, and then linear. So a visual analysis using GeoGebra lines up with what we found from our area under the curve analysis. For example, we see that when b equals 4.5, we've accumulated the maximum amount of area, and that corresponds with the maximum height of our area accumulation function. Going backwards in time, we can see that right where b equals 2, that's the integral from 2 to 2, our area accumulation function is down at 0, and we start accumulating negative values as we move backwards until b equals 1.5. So I've uploaded this applet so you can check it out yourself. I think that this is an important concept, and so it's something worth looking into and messing around with yourself until you have a good understanding of being able to do these types of graphical analysis without having to come up with an equation each time for each of the functions.